And on to 2.1. So this first video is going to be about increasing, decreasing, and applications, and then the last video will be about piecewise functions. So increasing, decreasing, and constant functions, all we're looking for is the intervals over which the function is increasing, which means rising from left to right, and the intervals on which the function is decreasing or falling from left to right. So we're always reading like we do a book, left to right. So if you look at this graph, I'm sorry, and then the last word is constant, which means not changing. So if we look at this graph, you can kind of make it into segments. There's segment 1 where something's happening. There's segment 2 where something's happening, segment 3, and segment 4. And so we're going to look at what's happening over those 4 intervals. So the first interval is here from -1, 2, 3, 4 to here, which is -2. So something is happening between -4 and -2. The graph is rising from left to right, so we're going to say the graph is increasing. So it's increasing over the interval -4 to -2. Section 2, nothing's changing, which means the graph is staying constant. So the graph is staying constant between -2 and 0. So the next section was -2 to 0. Now we're going to look at the next interval, which is from 0 to 1. So from 0 to 1, what's happening to our graph? Well, again, it's rising from left to right. So we'll put a U, and then we'll say from 0 to 1, the graph is also rising. And then lastly, we've got from 1 all the way here to 1, 2, 3, 4. And what is the graph doing? Well, it's falling from left to right, so it's decreasing. So it's decreasing over the interval of 1 to 4. And so you'll be asked questions exactly like this. They'll give you a graph and then you just look at the intervals. Always use round brackets, never use square, because at the point of change, it's neither increasing, decreasing, or constant, it's changing. And so we'll always use round brackets, and then you're just looking for the segments. What segments is it rising? Which segments is it falling? And which segments is it remaining the same, or increasing, decreasing, and constant? The next couple words are relative max or min. So this graph or this textbook talks about there being relative max or mins. What it is it's anywhere your graph has a turning point. So something where it's changing from rising to falling or falling to rising, you are getting a kind of a turning point, really. And what the turning point is it can either be a maximum or a minimum. It's a maximum if it's the highest value is the turning point, and it's a minimum if the lowest value is a turning point. Okay, so if you look down here, right, this is the highest point in a turning point, and so it's a maximum, and this is the lowest point of a turning point, and so it's the minimum. Now here's the weird part. We don't just say points. We're not like, okay, well the maximum is -1.09 and 4.05. Instead we say it's a max of 4.05 at x equals -1.09. So it's very specific language they use. So it's a y value of 4.05 when x is -1.09, but instead of saying a y value, we say a max. So it's a max of 4.05 at x equals -1.09. Okay, I want you to pause the video and see if you can write that sentence for the minimum. So hopefully you found that it's a minimum of -2.34, oops, that's a 4, at x equals 0.76. Okay, so before we move on to applications, I just want to go back here for a second. I just had this thought. I was like, you know what? I was just automatically kind of going into domain mode, and I put the OR symbol here, and it's not increasing over the interval from -4 to -2 or 0 to 1. It's both of those. So you could use AND, which an AND symbol is the upside down union symbol, or I just went to quickly look in the textbook to see what they did, and they just put a comma. So it's increasing over these two intervals, it's decreasing over this one interval, and it's constant in this one interval. Okay, sorry, being picky. All right, last thing before we take a bit of a break is applications. So we've already kind of done applications of functions. We looked at that at the end of 1.2. But at the end of 1.2, they gave you the equation. And in 2.1, they now want you to come up with the equation for the application. So it's going to give you something like one of the following two. So the first one is car distance. You've got Emma and Brant driving away from a campground at right angles to each other. So right away, I'm going to draw that. We've got one of them driving this way and one of them driving this way. Let's say that this is Emma and this is Brant. One thing you'll notice is I never draw to scale. Sorry, I feel like I should. I just realized that Emma's driving faster, so her line should be longer, but it's just a diagram for the purpose of a diagram. Okay, so we know that Emma's speed, so her rate of travel is 65 kilometers per hour. And we know that Brant's rate of travel is 55 kilometers per hour. What we want to know is the distance between the cars as a function of time. So this is the distance between those two cars. So you can already sort of see taking shape this right triangle. And hopefully you're sort of thinking of Pythagorean theorem. So you're not having to use the distance formula for 1.1. We're just going to use Pythagorean theorem. So we want to express Emma's distance and Brant's distance to find the distance between them as a function of time. So if you remember way back from other knowledge, is that distance is equal to rate times time. So for Emma, remember subscripts are always identifiers, so the distance that Emma travels would be 65 kilometers per hour for however long they both drive. So Brant's distance would be 55 t, right? So 55 kilometers per hour times however long they drive. So we're going to let t equal the time traveled. I won't insist on these let statements, especially if you use appropriate variables, but you have to know what they're representing. Now what we want to find is the distance between them. And so the distance between them is going to be Pythagorean theorem. So this d squared would equal Emma's distance squared plus Brant's distance squared. Okay, so now what? Well, let's put in what we know. Distance squared would equal Emma's distance is 65t, all squared. Brant's distance is 55t, all squared. Let's see if we can simplify. So let's keep it as d squared, and let's go 65t all squared. So I'm going to plug in 65 squared, and I get 4,225 t squared. And then I'm going to put 55 squared, and I get 3,025 t squared. Okay, so this is all equal to d squared. I'm going to collect like terms, and I get 4,225 plus 3,025 is 7,250 t squared. Now at some point we had to realize that we were solving for d and not d squared. So we could have done that way back up here. I just kind of am rolling with it and doing it differently than I did it even in my notes I'm looking at. But I'm going to now solve for d. So I don't want to know the distance squared between them. I want to know the distance between them. Now technically anytime you take a square root, they should always be a plus minus, if you remember that from solving squared equations. But because this is a distance, we're going to reject the negative. So reject negative solution because it's distance. So we're going to say the distance is equal to the square root of 7,250 t squared. Now, I had to go look to the textbook to see what they did now. You know, it's kind of one of those random things where it's like, okay, what are they going to expect from me now? And different solutions are always kind of given in different forms. So even though this question never said, you know, round to the nearest tenth, they had that expectation. So, you know, sometimes you're going to get to a point like this and you're going to be like, all right, am I done? Am I not done? What more can I do with this? So if I was looking at d equals the square root of 7,250 t squared, I'd be thinking either simplify my radical to give an exact solution, or I'd be thinking of touching my calculator. And I think the textbook is at this point saying, hey, just touch your calculator, it's fine, because we haven't talked a ton about radicals yet. So just so you're getting the same answers at the back of the book, we're going to take the square root of that answer, and I get 85 point, let's do it to the nearest, what does the textbook do? Let's do it to the nearest 2 decimal places, so 0.15. And then the square root of t squared is t. Now you'll notice if you are reading along with the textbook, they start with the absolute value of t. Because time is not going to go backwards, and because whenever we take a square root of a square, we know that we're going to take the positive case. So it's just going to be 85.15 t. So this is, now careful, this is distance equals 85.1 t. But if I want to express distance as a function of time, I'm going to change it to function notation. Distance as a function of time is equal to 85.15 t. Awesome. All right, next example. Oh, and before I go there, I guess I should put in that t has to be greater than or equal to 0. They had all these questions where they expected you to sort of know what the domain would be, right? The domain is 0 to infinity. And you'll notice I kind of took that off of most of the questions I asked because, you know, it's kind of like a, should you know that thing at this point? I don't know. And so for me, I'm looking at, can you set up a function equation? Can you use the information given, A, to come up with an equation? And then can you realize that to put it in function notation, we have to do it as d is a function of t, or d is a function of x, or whatever you're going to let your variable be. All right, so let's look at another equation that we need to set up. This one is area. So I'm trying to stick with equations you'd know. Pythagorean theorem, you should know. Area, you should know. So a community college has 30 feet of dividers with which to set off a rectangular area for a student testing center. If a corner of the math lab is used for the testing center, the partition need only form two sides of a rectangle. Express the floor area of the office space as a function of the length of the partition. So we're trying to come up with an equation of area as a function of length. But we have to figure out what we're going to be able to use for variables and how we're going to express it. So the first thing you have to realize, and this I had to actually look at the book picture because I was like, what are they saying? What they're saying is they're going to partition off a corner of a room. So you are going to have two walls on two sides, and then your partitions or your dividers are going to make up the other two walls. So what I said is, okay, well, I want to write area as a function of length. So I'm going to let this side be length. Now they told me that I have 30 feet of dividers so that I could write width in terms of length. So this is length, this is width. So the length is L. And you know what, I often like to write it in the other order. So I'm going to put length is L. Width, I don't want a second variable, so I want to find a way of writing width in terms of length. Now I know I have 30 feet to make up the length and the width. So if I wanted to express width as an L, I would subtract L from both sides and I get 30 minus L. So width is 30 minus L. Now I want to write an equation for area. Area of a rectangle is equal to length times width. So now I've already kind of done this, and maybe you could have written this out first and been like, oh no, I've got area as a function of length and width. I need to replace one of the variables. What other information did they give me? And then you go searching, or you look ahead and be like, okay, I always know I have to write one in terms of the other and then put it into my equation. So I'm going to put L as L, and then I'm going to put W as 30 minus L. So area is equal to the length times 30 minus whatever that length may be. To simplify this, I'm going to multiply the L through. I get 30L minus L squared. Now personally, I would rather see that as negative L squared plus 30L. I like to write things in descending orders of power. And then this is what area equals. But to write area as a function of length, I'm going to write it like that. Now again, if you're looking at the textbook, they write area as a function of x. I prefer to use variables that I don't have to guess what x is. Is x width? Is x length? I don't know. But this would be the answer for part A. Part A is just express the floor area as a function of the length of the partition. Sweet. There is a part B in the textbook that again said skip because it was talking about the domain. If you're looking at that and you're curious, you know, if you only have 30 feet of dividers, we're looking at restricting the length. Well, if you only have 30 feet, then L has to be less than 30, right? And you can't use negative lengths of dividers, so it has to be between 0 and 30. But don't worry about part B, don't worry about that domain thing. Really, I'm looking for, can you set up an equation with known information? Okay, and make it functional. All right, and then the last question, I just kind of wanted to relate this back to the idea of relative max and mins, is it says, using the graph below, determine the dimensions that maximize the area of the floor. So you're looking for a highest turning point, which is here. Now, some of you might be going, hey, that's the vertex. Awesome. Yes, we could solve it. We'll do that in a later chapter, but for now, you'll be given graphs. So we're going to say that there is a max area of 225, right? Because the y scale is area versus the x is length, when the length is 15. Okay, because they used x, but my x was L, so when the length is 15. So it says, what dimensions will maximize the floor area? Well, if the length is 15, the width is always 30 minus the length, so 30 minus 15, and the width is 15. So therefore, we like to answer word questions with word answers. Therefore, the dimensions that maximize, oh, I can't write, floor area are 15 by 15, do we know the units? Feet. Sweet. Okay, so that's the end of this section. Now, I just realized that there was something I wanted to mention back here that I forgot. It's the idea of this word relative. Okay, determine any relative max or mins. I just want to make sure that you guys are clear is that relative max or mins, they're not the absolute top or bottom of a graph. Like this graph goes beyond that max and it goes below that min. So these aren't absolute max or mins of your graph. That's why they use the word relative. All right, good luck with the start of 2.1.